Greetings to everyone around the world. Welcome to the SMT session on artificial intelligence and machine learning. We are very happy to have you here. Our first presentation is from Seifide Azimi. She is a PhD student from American University of Tehran. Ms. Azimi is working on radioxenon data. Her field of studies is nuclear engineering and artificial intelligence.
Hello everyone, my name is Seifide Azimi from American University of Tehran. Welcome to my presentation titled Beta-Gamma Coincidence Radio-Xenon Spectra Classification using the Convolution Neural Network Technique. I am starting my presentation with introduction, and then I will go through methodology, and finally I will present my results and I will conclude. International monitoring systems can detect the amount of radioxenon in the atmosphere. Finally, I will present my results and I will conclude. International monitoring systems can detect the amount of radioxenon in the atmosphere by sampling and measuring activity concentrations of different radioxenon isotopes in order to identify and prevent any nuclear test explosion. Concentrations of approximately more than 60 samples are measured every day based on the collection time of 3 types of radioxenon systems in 12 or 24-hour air samples in completely operational 40 IMS noble gas components. The next generation of noble gas systems will have higher time resolution and more samples are created per day. Further build-up of the network will also increase the number of samples to be analyzed every day. A categorization scheme is needed to screen out samples that are uninteresting in the CTBT context. Analysts need to review and screen samples to distinguish subsequent civilian sources from a nuclear explosion. As you can see in this figure, radioxenon is categorized into 3 levels based on activity concentrations. For each sample, the threshold of the anomalous concentration is updated. It is obtained with a special formula from absolute activity concentrations of all samples of the previous 365. Level 1 represents no detection of radioxenon, while level 2 shows that radioxenon is detected, however at a normal concentration level. Level 3 indicates that radioxenon is detected and at least one concentration is above the abnormal threshold. The analysis method currently employed by the International Data Center, known as netcon calculation method, was developed around 15 years ago. Over the past several decades, artificial intelligence has been growing fast with numerous practical applications and active research topics. Categorization is important to screen the samples to focus only on the important samples that might be associated with a nuclear explosion, to enhance the automatic processing and keep the workload of the analyst of the IDC at the current level, and also to assist the national data centers in day-to-day and manual review of samples and identify those significant ones that could possibly be associated with a nuclear explosion. In this study, for the first time, we present a machine learning perspective in categorization beta-gamma coincidence of radioxenon spectra based on real data. To conduct our analysis, we utilize experimental raw data derived randomly from USX75 measurement station between 2012 and 2019. Each sample is originally in the form of a two-dimensional matrix 256 by 256 beta gamma coincidence. Values at coordinate indicate the number of counts that are simultaneously recorded in detectors. As you saw in categorization scheme in slide 3, in our research, we combined level 2 and level 3 to categorize radioxenon according to the presence or absence of radioxenon in each spectrum to find background spectra. Also, we classified level 3, which contains atypical concentrations of radioxenon isotopes, from level 2 and level 1 to predict the existence of xenon with high activity concentration. This figure shows the overall workflow of our method. We tested several models, and it is expected that using convolution neural network is more effective than other learning machines due to the complexity of the input data in distinct levels. We created deep convolution neural network model, which consists of 3 sets of two-dimensional convolution layer with two-dimensional maximum pooling, followed by 2 dense layers with a dropout and a flattened layer. Also, each convolution layer has a leaky rectifier linear unit activation. Our results demonstrate that convolution neural network model can discriminate background from other levels with accuracy of 92%. Accuracy is a measure for how many correct predictions the model makes for the complete test dataset. Learning curve indicates a gradual increase in the accuracy of classification for training data with an increasing number of epochs, implying that models are learning from data. The loss score represents the total number of errors that the model predicts, and here is about 0.2. Confusion matrix table indicates different performance parameters on test data, including precision, recall, F1 score, sensitivity, specificity, and average sensitivity for background sample identification is 94%. Results show that level 3 could be distinguished from level 1 and level 2 with an overall accuracy of over 98%. Fluctuation in model loss validation curve reaches a constant number in successive epochs. Average sensitivity for anomalous samples identification is 96%. In model loss validation curve reaches a constant number in successive epochs. Average sensitivity for anomalous samples identification is 96%. Results imply that properties of level 3 compared to level 1 and level 2 are more distinct. We can conclude that deep learning model can be utilized as an important pre-screening method to highlight relevant samples prior to their interactive analysis to be used for prioritization of work assignment by analysts. This is possible to use deep learning algorithm to well distinguish anomalous spectra containing large amounts of radioxenon and to detect background spectra by analyzing the entire real raw two-dimensional spectra. The classification analysis can be conducted without needing information such as background data, interference contributions from other radionuclides, abnormal limit measured for each spectrum, and consecutive isotopes, and also calculating activity concentrations.
Thank you very much for this wonderful presentation. We are now ready for questions. So if you have a question, please write. It's really wonderful. Okay. So we are now going to the second presentation, which will be by Geeta and Nima Arora. Geeta is a seasoned software developer, and she is currently responsible for maintaining and developing NetVisa. Nima is an artificial intelligence researcher who co-invented NetVisa. So we're very much looking forward to this presentation as well. So Nima, you have the floor, virtual floor.
Hello everyone, I'm Geeta Arora and today I want to talk about a new way of calculating the origin error estimate for NetVisa. Some background first. NetVisa is a network processing software that builds event bulletins from seismic, hydroacoustic, and infrasound arrivals. It is based on a generative model that includes a prior on the event location, a likelihood model of arrival attributes given the event location, and a model of noise arrivals and coda arrivals. It uses all this to perform a heuristic search-based inference. NetVisa has shown promising results comparable to the human-reviewed bulletin LEB, despite the fact that NetVisa doesn't create new arrivals unlike human analysts. In this figure, you can see that NetVisa had the highest overlap with the ground truth for these events from 2013. NetVisa performs a heuristic search-based inference to compute the best event location, also called the origin. How does it do that? For every point on the longitude, latitude, depth, time, and event size dimensions, it assigns a score that reflects the likelihood of the event being located there, given many factors like the detection or the lack of detection, or likelihood of noise, etc. The point with the highest score is chosen as the likely origin. The map here also shows the contours for each score and reflects the uncertainty of the event location. These contour maps can get complicated for many reasons. In this example, at some location, the associated detections are not possible. For example, a P phase cannot be detected at 105 degrees. This leads to sharp drop in contours for events with large number of detections, as you can see with these dark lines in this map. After NetVisa determines the position of the origin, it calls liblog to compute the error ellipse. The error ellipse represents the uncertainty in the event location. The problem is that as part of computing the ellipse, liblog often relocates the event to a suboptimal location. For example, in this picture, NetVisa computed the event location here, And LibLock relocated it to the red circle, and this is the error ellipse, and the ellipse doesn't even include the ground truth location. The reason LibLock moves the event is because it doesn't have the joint probability distribution of the event and its associations. Our goal is to use NetVisa to estimate the error ellipse in order to avoid moving the event location. Now, the concept of an error ellipse has a built-in assumption that the uncertainty is represented by a bivariate normal distribution, like the ellipse right here. However, our contours here are not ellipses at all, as you can see in this picture. So the challenge is, how do we represent the contours with the closest bivariate normal distribution? This is our high-level approach. Our goal is to convert the NetVisa posterior distribution, which is the contour, into the bivariate normal distribution, which is an ellipse. Now the steps here include defining the proposal distribution to fully cover the posterior. And this proposal distribution is a uniform distribution within a ball of a certain radius. Then we draw samples from the NetVisa's posterior distribution. We use those samples to estimate the eigenvalues using importance sampling, where we weigh the samples according to how close they are to the posterior. And we use those eigenvalues to estimate the 90% error ellipse. Let's look at each of these steps in detail. Step 1 is to define the proposal distribution to fully cover the posterior. Here we start with a small radius around the origin, like here, and we do random sampling of points at that distance in all different directions with varying depth and time. We keep expanding the radius till we find points at any azimuth which have the probability of having the event there at least 1% of the probability of the event being at the origin. So in this example, this contour here marks the boundary of our big ball. The picture here shows distance range, and we do similar ranges for depth and time. The next step is to draw samples from the NetVisa posterior distribution, which are simply drawn uniformly at random from the distance, azimuth, time, and depth space. And we draw 10,000 samples to get a stable error ellipse. After that, we estimate the eigenvalues using importance sampling. Here we have to assign a weight to every point that we drew. And this weight is the posterior probability of the event being located at that point. We then normalize these weights so that they all add up to 1 and use those to compute the 4x4 covariance matrix in the x, y, depth, and time dimensions. And from the xy portion of the covariance matrix, we compute eigenvalues and eigenvectors, which are like those in this ellipse, right? So these would be the eigenvectors. And we use that to estimate the 90% error ellipse. So here, this is the semi-major axis, this is semi-minor axis, and the angle from north is the stripe. Well, we got some promising results. Remember that LibLock's computation of the error ellipse was moving the event location? Well, that got fixed. And in this first picture on the left, this was the event location that NetVisa found, and this is the error ellipse that NetVisa found. And the ground truth location is within the NetVisa's error ellipse. So that was good news. Now, in this picture on the right, you can see that the contours are a lot more complicated. In this particular contour here is almost disconnected from this main contour here. And the ground truth event unfortunately lies in this disconnected contour. So even though we did not move the event location, the error ellipse that NetVisa found still does not contain the ground truth event. Now we tested this approach on all of 2016 ground truth GT5 data from ISC. In both of these graphs, the x-axis represents the number of time-defining phases, which we call NDEF. The good news is, in the graph on the left, you can see that the final event found by NetVisa is consistently closer to the ground truth event compared to what LibLock was doing. Well, now to the bad news. Well, the term 90% error ellipse means that 90% of the ground truth points should be within the ellipse. Now, the percentage of points within the ellipse of the NetVisa's computation here, as you can see, is consistently like below 30%. In fact, the overall percentage is just 25%. Even though it's better than LibLock, it is hardly anywhere close to 90%. So we decided to refine the NetVisa model further. The model is actually not trained on the ground truth event at all. It is trained on LEB. As the graph here shows, the LEB events can sometimes be hundreds of kilometers away from the ground truth event, especially for low number of associations. So we changed the model training to account for this inaccuracy. And the results really improved. Here is the example that we looked at before, the one with disconnected contour lines. With our existing model on the left, the ground truth was outside of our error ellipse because it was in its own little contour, which was disconnected from the main contour. However, with the new model on the right, the contour lines are a lot smoother and the error ellipse expands to include the ground truth event. Here is another event with just 2 detections. The NetVisa error ellipse is much closer to the ground truth here with the existing model. See, the LibLock was so far away. However, it still doesn't include the ground truth. What's more troubling is that these posterior probability distribution lines don't include the ground truth either. But with the new model on the right, the posterior distribution captures the uncertainty much better, and we are able to get the ground truth inside the error ellipse. Now, granted that this ellipse is much larger than the one before, but that is expected given that this event has only 2 time-defining phases. Here is how the different approaches perform on the 2 nuclear explosions that happened in North Korea in 2016. This is the explosion from January, and both the existing model on the left and the new model on the right capture the ground truth event well with the error ellipse. And this is the event from September 2016. And even here, the NetVisa error ellipses capture the ground truth event very well in both the cases of the existing and the new models. Now, these graphs show how the 3 models compare to each other. The new bars are the green bars with the new NetVisa model. And as you can see in the graph on the left, the event location of the new model is on par with the existing model, which is in blue. So the event is not any further or any closer in general to the ground truth compared to the existing model. The graph on the right is where all the action is. So you can see that the percentage of points that are within the 90% error ellipse almost double from 25% to 45% from the old model to the new model. Time for some more detailed analysis. These graphs plot the percentage of points for different approaches at different confidence ranges for distance, time, and depth. An ideal approach would coincide with the dotted green line right here in the middle. This line represents, for example, that 60% points should lie within the 60% error ellipse, 20% points should lie within the 20% error ellipse, and so on. The first graph here is for the distance. It shows that the orange line here for NetVisa and the green line here for LibLock are both so much worse compared to the red line here, which is for LEB. Now, LEB, remember, is the Human Reviewed Bulletin. However, the new NetVisa model in blue is comparable to LEB. The second graph here is for time and has similar results to the first one. The third graph here is for depth. And here the new NetVisa model is very close to the ideal dashed green line. To get more ground truth events inside the error ellipse, the ellipse size does go up, as you can see here. For example, for NDEF equal to 2 to 3, the orange bar shows the semi-major axis for LibLock, which is approximately 115 kilometers. Remember, it only had 25% of the points within the error ellipse. With NetVisa computing the error ellipse here in blue, the semi-major axis size goes down to approximately 75 kilometers, but with the same result of 25% of the time points being within the error ellipse. With the new NetVisa model, which gives 45% of the points within the error ellipse, the semi-major axis size now is approximately 125 kilometers. In conclusion, We have updated NetVisa to compute origin error ellipse without using liblock, and this gives us an improvement in the event location. We have changed the NetVisa model to account for uncertainty in LEB event locations, and this gives us much better calibrated error ellipses and posterior uncertainty. And NetVisa error ellipses are now on par with LEB. We have completely fixed the uncertainty for depth. However, there is some future work cut out for us here. Firstly, only 45% of the ground truth points are within the 90% error ellipses. So we need to improve our model to account for further sources of uncertainty so that we can bring this number closer to 90%. Secondly, as we see in this picture here, an ellipse is not a best way to capture the posterior distribution. The contours in this ellipse are not even convex, they're like banana shaped. So we are actually, by using ellipses, we are wasting so much area here that we are searching, which we don't need to. We need to find new ways of representing uncertainty. Thank you so much.
Thank you, Gita, for this wonderful talk. It has been really a great pleasure to follow your work in EMARS with Ronan and Ruki over the years and development of NetVisa. Please note that all the questions will be after all the presentations are finished. And I also would like to tell everyone that so Q&A is open, so please send your questions in, and we will then provide answers after the presentation. And you can also write to whom is the question. Yes. So then it's my pleasure then to introduce the next speaker, which is Dr. Myers. Dr. Myers' research focuses on nuclear explosion monitoring with emphasis on technologies that improve the accuracy of event locations and characterization of uncertainty. Dr. Myers led the development of the bias lock method for simultaneous relocation of many seismic events and assessment of data quality. His interest is in basic Earth science, particularly regional and whole Earth structure. So, Dr. Myers, it's your virtual floor.
Computationally efficient emulation of full physics calculations is an important application of artificial intelligence and deep learning methods. It is this type of application that I will be talking about today, and specifically, it is the application to seismic phase travel times computed using a global three-dimensional model, with the goal being to speed up the calculation so it can be used in an operational system or interactively by analysts. Over the past decade, a number of models have been developed to improve the accuracy of travel time predictions. In this case, we use the LLNL global model. You can see in the lower left that the LLNL model is the focus of 4 publications, and these publications cover the methods used to compute travel times, image the Earth's interior, and data sets that include many body wave phases and now surface wave dispersion and group velocity. Also included in the publications are validation tests that demonstrate improved monitoring performance when the model is used. A link to the openly available model and codes that can be used to access the model and to compute 28 seismic phases that are commonly used for seismic monitoring is also listed. These phases are listed on the right. The yellow lines shown in the cross-section are seismic ray paths for first arriving P. These paths are governed by differential equations that do not have a closed-form solution in a generalized 3D model. Determining these ray paths is the largest computational cost in computing travel times. 3D models improve travel times by accounting for deviations in Earth structure from spherical symmetry. These charts show the improvement in travel time prediction accuracy and improvement in seismic event location when the 3D model is used. The chart on the left shows travel time error as a function of event station distance with respect to ground truth data. The black line represents error when the standard spherically symmetric Earth model is used. The red line is travel time error when the global 3D model is used, and the dashed blue line is percent improvement when the global 3D model is used. Note that improvement is generally 30 to 40%, and improvement reaches over 60% at regional distances, which is event station distance out to 25 degrees. The center chart is event epicenter error in kilometers as a function of the number of global P waves. The black line is error when the spherically symmetric model is used to compute travel times, and the red line shows epicenter error when the global model is used. Again, the dashed blue line is percent improvement, which is about 30% when the global 3D model is used. The chart on the right is similar to the center chart except for regional distances. Improvement of seismic event location estimates is highest for regional distances, with percent improvement reaching 40 to 70%. We are not routinely using 3D models because of the computational cost of computing ray paths. For rays that primarily travel through Earth's mantle, teleseismic distance, ray paths do not deviate too much from ray paths determined with a spherically symmetric model. Therefore, travel times can be computed relatively efficiently, about 1/10 of a second on average. However, for regional phases, Earth's structure is more complex, and rays that take significantly different paths can arrive at close to the same time. This is shown in the chart on the right, with black lines representing the earliest arriving rays and dashed lines representing rays that arrive within 2/10 of a second of the fastest ray. Because many ray paths have to be tested, computation time for these rays can take over a second. Locating a typical seismic event using IMS data can involve tens of phases and several iterations, and the computational time for computing travel times can be tens of seconds, which is too slow for operations and iterative analysis. For these reasons, we have developed a computationally efficient machine learning method to emulate travel time calculation through a 3D model. Our approach is to compute hundreds of millions of travel times that are then used to train a machine learning model. An example of travel time predictions is shown on the left, where differences between spherically symmetric and 3D model predictions for about 1 million rays are shown for a station in the United States. We then use the pre-computed travel times for stations around the globe to train a network, but more on that in a moment. Then we use the trained network to compute travel times for arbitrary event and station locations, and eventually for any phase. After testing many machine learning approaches, we found XGBoost is the simplest one that provides equivalent results to much more complicated methods. XGBoost is an open source software library that provides a regularizing gradient boosted method for many languages including Java, Python, R, and C++. XGBoost is fast compared to other gradient boosting methods, and it typically has superior model performance. Training that required days on hundreds of computer cores is accomplished in hours on a few cores using XGBoost. It's the go-to algorithm for Kaggle competition winners dominating regression problems on tabular datasets. Gradient tree boosting is a machine learning technique that produces a prediction model in the form of an ensemble of decision trees. Successive decision trees are trained on the residuals of the previous tree, and optimization can be guided by an arbitrary differentiable loss function. In order to develop universal prediction capability, we develop a training set that starts with over 25,000 stations listed in the International Seismological Center database. The ISC database is reduced by removing stations that are within about 1/4 degree or 25 kilometers of one another. That results in over 10,000 stations being used for training, and the map in the lower left shows that the station coverage is still very good. Training is divided into distance ranges so that machine learning can exploit approximately stationary covariance of differences between 1D and 3D model predictions. Event sampling is dense for distance ranges where differences between 1D and 3D models change over short distances. That's shown in the figure in the center on the bottom. This is for a station in Texas in the United States, and you can see that there's dense sampling near the station, slightly less dense sampling at regional distances, and still lower sampling density at global distances. Input parameters, event latitude, longitude, and depth, and station latitude, longitude, and elevation are normalized by taking the sine and cosine of latitude and longitude values. This step makes latitude and longitude parameters continuous around the globe. We use 90% of the stations to train the XGBoost system. 5% are left out and used for further tuning of the system. The remaining 5% of stations are used for testing. Note that stations used for testing are not used in training in any way. So this test is particularly difficult, and it is applicable to a case where the method is applied to a station that the method has never seen. We divide validation results into 3 distinct distance ranges: local, regional, and teleseismic. This chart shows results for the local distance range, which is out to about 1.5 degrees, and the following charts follow a similar format. The graph on the lower left shows error as a function of event station distance. Importantly, error is relatively constant or stationary over the distance range. Moving to the upper right, we use mean absolute error as a general metric for prediction error. For stations that are used in the training, the error is about 0.153 seconds. For stations that are not used in training, the error is about 0.26 seconds. Both of these values compare favorably with the estimated error of the 3D model itself, 0.6 seconds, which is based on differences between model predictions and the ground truth data. The point here is that error attributed to the machine learning method does not add significantly to the error budget. We also include the importance XGBoost puts on input parameters. We see that event station distance is the most heavily weighted at local distance, which is almost certainly because global models tend to be biased for any particular locale, and adjustment based on event station distance corrects for that bias. Moving to regional distance, 1.5 to about 20 degrees, we see a little bit more non-stationarity in the lower left graph. That's probably due to greater complexity at about 15 degrees. Median absolute error for stations used in training is about 0.382 seconds. That bumps up a little bit to about 0.417 seconds for stations not used in training. And again, that compares favorably to the error of the 3D model. Again, due to global model biases, the 3D distance is the most important parameter. And we see in the lower area of the plot that the number of samples used in training and validation is in the millions, so these are very robust results. Last, for teleseismic distance, or about 20 to 98 degrees distance, we see that travel time error is approximately constant as a function of distance in the lower left graph. That is a very desirable result. The mean absolute error for stations used in training is about 0.321 seconds. For stations not used in training, the value of error is about 0.36 seconds. Both of those numbers, again, compare favorably with the average error of the 3D model, which is about 0.4 seconds for teleseismic distance. Note that the XGBoost places most importance on event latitude and longitude. So unlike other distances, event station distance is no longer the most important parameter. And this is due to the fact that global models are relatively unbiased at these distance ranges. Again, note the number of samples is used for testing is over 9 million. So again, this result is quite robust. So in conclusion, 3D models can significantly improve the accuracy of seismic travel time predictions. Computation time using a 3D model is too slow for operations. Tests show that machine learning emulation for seismic travel times are accurate to a few tenths of a second, which is lower than the inherent error of the 3D model. Computation time using a machine learning method is about 30 microseconds, which is well within operational needs. So with that, I'll stop and take any questions that you might have.
Thank you, Stephen, for this wonderful talk. And again, let me remind that we will have the Q&A session after all the presentations. So let us continue. So our next speaker, after receiving the PhD degree in mathematics, Yuri Bregman held several positions at the Latvian State University, at the Rīga Technical University, Latvia, and at the Haifa University, Israel. And since 1994, Yuri has been a researcher with the Zurich Nuclear Research Center. And since 2002, a researcher at the Israel NDC hosted by Zurich. Yuri's research interests include signal processing and machine learning in geophysics, especially the detection and characterization of seismic events. So Yuri, you have the virtual floor.
Hello, my name is Yuri Bregman, and the title of my presentation is Identification of Repeating Seismic Events Using Nonlinear Dimensionality Reduction. This is a joint work with my colleague Yochai Ben-Horin from Israel National Data Center and with Itai Niv and Neta Rabin from Tel Aviv University. Outline. First, I will give some introduction. Then I will explain diffusion maps, which is nonlinear dimensionality reduction method. And I will present 3 test case studies, including aftershock identification at local and regional distances and identification of arrivals caused by mine explosions. Repeating seismic events such as aftershock sequence or mine explosions make up a significant part of seismicity. Automatic identification of repeating events may lighten the analysis burden and to allow for timely production of reviewed bulletins. Moreover, small aftershock and local mine explosions may reduce the quality of IDC automatic bulletins, creating fake events. Therefore, it is desirable to identify or remove the arrivals of such small events prior to the IDC association process. In next 2 slides, I will explain our basic processing framework. It includes 3 stages, and at the pre-processing stage, we convert the original seismogram to an image named normalized sonogram. Then we apply the dimensionality reduction process using diffusion maps. And our final decision we make in the low dimensional embedded data space. Here is an example of normalized sonograms. We start with original seismogram. Here is an example of 2 seismograms. One of main shock with magnitude 5.2. The second one of its aftershock with magnitude 2.6. Of course, there is very huge differences in amplitudes. First, we apply spectrograms, but we can see that the energy distribution by frequencies is quite different. Then we compute normalized sonograms where the logarithm scale frequency bands are applied and the amplitudes are normalized in every frequency band. So we receive 2 images which are quite similar. Almost the original amplitudes were quite different. The next step is the non-reactive dimensional reduction. Diffusion maps is an unsupervised technique, does not use data labels. It constructs a global description of data set from local similarities. Actually, we convert our data to Markov matrix and compute the eigenfunctions, they actually are new diffusion coordinates. It's nice property of diffusion maps is that they preserve the distances of original data by defining a diffusion matrix. Without going into the details, let me explain the main idea with this very simple example. If you look of two purple points, that we can find many jump roads from one point to another on this green area. On other point, if you look on two black points, also they are very close in Euclidean space. Each road from one black point to other one goes through this narrow yellow bridge. So there is not so many roads from one point to black point to another, and actually they are not so close one to another as it looks using the Euclidean distance. So in diffusion embedding, you see that the purple points are closed and the black points are far one to another. The case studies. Our first example is aftershocks of 2004 Dead Sea earthquake. The dataset includes 1 week of waveforms of vertical channel of IMS seismic array Mount-Meron MMAI. As a template, only the main shock is used, which is supposed to be identified in advance. First, we apply detector, including Butterworth filter, followed by DeLTTa detector. As a result, we receive about 100 time steps. For each such time steps, the associated waveform were cut and aligned according to the arrival time. Using the diffusion maps embedding, we identified 51 aftershocks. 8 of them were new, not included in national catalog. Here, the points are colored according to the results of our manual analysis, while my main shock is dark blue, aftershocks are red, and the other detections, which we call false detection not related to the aftershocks, are colored in black. The next example is aftershock of Crete earthquakes, which was recorded at the regional distance at the IMS station Eilat. As a for the data set, we used 2 days recording, and we also used 2016 automatic arrivals of IDC, which were included in the IDC arrival table at the external data set. Again, seismograph main shock used as a single template for identification of related aftershock. The score based on the diffusion maps embedding were calculated for each such detected arrival. Here is a graph of the score. I will look in this zoom plot. Again, score of the main shock is black, is dark blue. IDC aftershocks included in LEB catalog are blue, and the earthquakes for other international catalogs, aftershocks for and other international catalogs are colored in green. Again, here is some misdetection, some false alarm, but over we're looking on the whole plot, we see that the most of the arrivals have very high score. Even the false automatic aftershocks from cell 3 has a relatively low score and is separated for the main cluster of aftershocks. Our third example is identification of arrivals from a specific mine. We used the data of IMS station Eilat again, which were caused, and we looked for arrivals caused by the explosion in Jordan. We have a lot of historical explosions recorded on this station. We took waveforms from as a training set from March 2011 together with 190 IDC automatic arrivals. The test set was about 3-week waveforms together with about 900 IDC automatic arrivals. Diffusion maps embedding of train set. We use 3 channels of Eilat station. In this plot, the historic explosions are colored green. Waveforms that do not belong to the mine are colored black, and the arrivals waveforms that belong to the mine are colored red. In this case, we used first 10 diffusion coordinates for our analysis. Here in this plane, you see only, of course, 2 first ones. Test case included, as was mentioned, about 3 weeks of data together with 845 automatic arrivals. In this plot of the test set is embedded in the first diffusion coordinates. Here, the points that do not belong to the mine are colored blue. The points that belong to the mine colored pink. The result, accuracy of 99% of our about 200 test IDC arrivals. Summary. Diffusion maps modeling is a robust method for automatic identification of repeating seismic events. The method was successfully applied to identification of aftershocks and mine explosions. Our future goal will be to develop a program that can be integrated in the IDC automatic processing for identification of repeating events. Thank you very much for your attention.
Thank you, Yuri, for this very interesting talk. We have now our last talk, so last but not least, is Alex. And Alex is a postdoctoral researcher at the University of Alaska at Fairbanks, working within the Wilson Alaska Technical Center. He graduated from Boise State University with a master's and then later a PhD in geophysics. Alex's current research focus is on atmospheric infrasound, where he bridges digital signal processing, forward modeling, and machine learning to monitor for large chemical and nuclear explosions. So, Alex, it is your virtual forum.
thank all of my collaborators from the University of Mississippi, from Los Alamos, from, of course, University of Alaska and Fairbanks, and from AvTech. Everyone on this project has been 100% instrumental, and we would have not gotten where we are today with this presentation without every single one of the co-authors here. So sincerest thank you to everyone on this project. And today, what I want to talk about is how we can use machine learning and infrasound to detect and classify events from either nuclear or large chemical explosions. And I don't think I have to, at least with this audience, remind everyone that large explosions do produce very energetic infrasound that can propagate hundreds and sometimes thousands of kilometers. And so to kind of demonstrate this and to also introduce the data that we will be using later on in this presentation, I wanted to show you the Humming Roadrunner experiments, which were a set of several very large chemical detonations that occurred in 2012 in the New Mexico desert. And one of these explosions, or most of these explosions were recorded regionally with infrasound microphones shown on as triangles on the left-hand plot. And the collected waveforms are now on the right. I want to point out that these two particular stations, which are, about 230 kilometers away, correspond to these two waveforms in the red rectangle. And without any filtering, without any array processing, it is very clear that those two traces have clear acoustic transients that are associated with this large Humming Roadrunner blast. And this is, all meant to motivate the fact that infrasound data can be and should be used as a monitoring tool. And this by no means is a novel idea. Obviously, the CTBTO and the International Monitoring System have deployed a global network of infrasound arrays, which are pictured on the left-hand plot here. And even though this network is relatively sparse, with some stations being located thousands of kilometers away from the closest one, each one of these stations has co-located microphones, meaning they're arrays, and we can leverage array processing to boost signal-to-noise ratios. Now, on the flip side of that coin, we also have many denser networks like the Transportable Array and the Alaska Volcano Observatory stations that were active last year in Alaska. And although these deployments are generally more dense, almost all of them contain one or a single channel, one microphone, meaning array processing is not possible. And this really motivates the research question that we're trying to address, which is, can we use single channel microphones to detect explosion signals from chemical or nuclear detonations? And if we were going to think about this in a very simplistic standpoint, we might say, okay, we have all of these single channel data. Let's just hire some technicians, and we will train the technicians. We'll show them examples of events, and we'll show them examples of non-events, and eventually they'll build up an intuition and be able to accurately classify data as it comes in. Obviously, there's a lot of problems with using technicians to do this, and actually, we can leverage machine learning technologies to accomplish almost the exact same goal. And we can, I can, in a very broad sense, say that the way we train a machine learning algorithm is very analogous to how we would train a technician. We show the machine learning model, in some cases, millions of examples of events, and we show them, perhaps millions of examples of non-events. And eventually, that model is going to learn the patterns associated with events and non-events and be able to accurately classify those data. Now, the problem from a machine learning context, and perhaps the benefit from a humanity context, is that there haven't really been that many nuclear detonations. According to the Arms Control Association, there's only been about 530 atmospheric detonations, of which there are fewer infrasound recordings on which we could train our data. And so this presented the main obstacle to our research is we want to use machine learning, but there isn't enough actual training data out there to train our models. And so what we decided to do was to actually generate our own data and use physical models to create our own catalog of synthetic events. And in the machine learning community, you might call this physics-based data augmentation, where we are creating new data from physical models. And in order to do this, we really need two things. We need sources, we need the actual signals that would have been produced from large explosions, and we need the atmospheres that those sources would travel through, because as the source travels through an atmosphere, it's going to get modulated by that atmosphere. Now, because this is a relatively new idea, at least in the infrasound community, we decided to really narrow the scope of this project, and we narrowed it down to the Humming Roadrunner experiments. So instead of looking at all the possible sources out there and all the possible atmospheres out there, we decided to model our sources after Humming Roadrunner data and model our atmospheres after Humming Roadrunner data. So the source time functions on the left-hand side are entirely synthetic. They're not recorded, but they are modeled after what we might expect from the Humming Roadrunner detonations. Similarly, the atmospheres aren't recorded somehow. They are modeled using the software AVO G2S, but they are modeled after what we might expect the atmosphere to look like during the Humming Roadrunner experiment at the same Latin long. And so now we can use these modeled sources and atmospheres, and we actually propagated 14 atmospheres through 50, we propagated 14 sources through 50 atmospheres in 4 different cardinal directions, north, south, east, and west, out to 10 distances from 50 kilometers to 500. And in doing so, we generated a total of 28,000 propagated waves. And one of those waves I've plotted here, and there's nothing, incredibly remarkable about it. It is a synthetic propagated wave. And in order to, for lack of a better word, make this more realistic, we decided to take randomly recorded data from the transportable array and add that randomly recorded data to that propagated wave to create what we consider a synthetic event, which is this last waveform plotted in yellow. And without going into any details, we used these 28,000 synthetic data to train a machine learning model. And when we did that, we found that it worked reasonably well. In fact, 90% of the time, it was able to identify those synthetic events correctly, and it was able to identify randomly recorded noise correctly. Now, perhaps that's not the most robust result. These are indeed synthetic data, and it's not necessarily going to be accurate or the same accuracy might not apply to real data collected in the field. But remember, we have the Humming Roadrunner experiment that we can test the model against. So you've seen these data before. These are just one of the explosions from Humming Roadrunner. And now when we apply the machine learning model to it, we can make a plot that looks like this. And here, this is still a time series plot, but now the amplitude corresponds to the probability that an event is occurring at that particular time at that particular station. And you see these boxcar type functions where the peak in boxcars would correspond to a high probability that an event is happening. And the machine learning algorithm didn't detect an event on all of the traces. Some of them are very flat, saying 0 probability of an event. And there's other reasons for that. Some include the fact that the noise can be quite high on some of these data. Some of these stations were located in shadow zones and actually didn't record any signal. But nonetheless, 5 of these stations, all the way out to more than 500 kilometers, were recognized as having an explosive transient cross that microphone, which I think is a really important and powerful result. And so to sum up here, the real 2 take-home messages I want everyone to put in their pocket before they leave is that we were able to train a machine learning model on entirely synthetic data, and it worked quite well on both the synthetic, in classifying the synthetic data, as well as classifying real-world data from Humming Roadrunner. And then broader than that, I really hope that this research will help elevate the usefulness of single-channel microphones, single-channel infrasound deployments, and increase the value of them as monitoring tools for nuclear and chemical detonations. And with that, I'll say thank you and take any questions.
Thank you so much, Alex Witzel. We are very grateful for this wonderful presentation. And we are finally going to read the questions. And first of all, let me just say we are so grateful that you already have a chat in the WebEx, and the questions, some of them are already answered. However, we are looking at the super event questions. And because we have a very short time still until the end of the session, we had to actually choose two questions. And for the rest of the questions, please go to the super event and then look at the program. And then you look at this, you look for the session 3.6, and under session, you will find all 5 talks. Under each talk, you can ask a question. So if when you select the talk, you can then you directly write the question to the author. So we are going to read then 2 questions. So first one is from Megan Slinkert. This is the question to Nima, and she says, very promising results and very nice talk. Can you remind us again how you created the new model?
Hi Megan, nice to hear from you. And thank you, Vera, for organizing this session. Yes, the main difference with the new model was the realization that the LEB data that we are training contains a lot of unmodeled location errors. And essentially what we have done is for every data set that we train from our model using our existing training procedure, we simply account for the fact that the LEB location itself may be incorrect by up to 100 or 200 kilometers, depending on the end number of time defining phases. And so we take that uncertainty into account with all the models that we train using the LEB location. For example, the arrival time, amplitude, everything is taking this uncertainty into account. So the uncertainties of all of those resulting downstream models get adjusted accordingly.
Thank you, Nima. Thanks, Vita. And thank you also, CBD, for answering some of the questions on super event already. And now the second question is for Steve. It is from David Bowers. David is asking, have you looked at the PKP, also teleseismic PKPs and SPP times predictions for deeper earthquakes in different subduction zones? So this is a question.
Yes, thanks, and I appreciate that. At this point, we've only looked at the first arriving P wave for this study. We have looked in other results that I haven't shown here today, and the approach appears to apply to additional phases as well. Getting to the issue of subduction zone events, so you have a depth effect on travel time. These results do incorporate depth effects for events down to 660 kilometers, which is the deepest known event. So those results and effects on depth are included in the results that you see today at all distance ranges, including local distance ranges. I hope that answers the question.
Thank you, Steve, for your answer. Since we do have time for another question, this is for now Alex Witzel. The question is by Sarah Albert. She says, hi, Alex, nice presentation and results. What ML model did you use? What frequency did you use for the waveform modeling?
So yeah, that's a great question. We used a simple artificial neural network for the actual machine learning model. It was very, very
It's just open. Since we lost Alex, we just wait for a second if he comes back.
Have you still lost me, or can you hear me now?
Yes, unfortunately, we lost you. If you can please repeat the answer. I apologize.
No, that's okay. I'll be very brief because I know we're it's basically the most simple machine learning artificial neural network model that we could possibly use. And the idea was that we wanted to use a simple artificial neural network to test the integrity of the training data. And I can go into more detail about the model in the chat if need be. And then the frequencies that we used were, we filtered the data very broadband. I think it was between 0.1 and 10 hertz, basically the general infrasound range that is typical in atmospheric detonation detection. So we wanted to keep the data as broad and the model as simple as possible, again, in order to really test the validity of the training data. Again, that synthetic data.
Yuri. Okay, now we have a question for Yuri by John Lee. It says, thanks for your nice presentation, Yuri. Do you compare your method with cross-correlation methods?
You see me? You hear me?
Yes.
Yes, in our papers several years ago, we showed that our method can actually exclude false detection of correlation method. But actually, I think that this method can be used together with cross-correlation method as some kind of post-processing in order to just to eliminate false detections.
Thank you so much for your answer. And I think let's find then a question for Sepide. Sepide was very kind and already replied some of the questions. So maybe we can find first one. So by Matthias Auer, we have a question for Sepide. What was done for, oh, thank you so much that you can hear us. What was done for data pre-processing?
Can you hear me?
Yes, yes, now we can hear you.
Yeah. We only standardized and normalized our data and then applied our method on the raw beta gamma coincidence histograms.
Thank you so much. And again, thank you also for answering other questions. And now for everyone, it is possible to write directly then to the contributors of the e-poster or the presentations in posters. If you just go to the program and select so 3.6 for artificial intelligence, and then I'm sure you have many more questions, but unfortunately we do not have much more time. So we are very grateful for all our presenters, and we are very grateful for everyone who's listening. Hello, Megan. Hello, everyone. So goodbye also. So we are then I think finished for today. Thank you so much.